So we're going to talk about the roles of computers. So the title of today's class is Roles of Computers in Drug Discovery. So today I'm going to talk about some recent example of drug discovery, and based on that, I'm going to talk about how computers are used in drug discovery. So, if you have any questions, during the class, just don't hesitate, and you can ask questions in Korean, of course. So, pharmaceutical industry can be our next economic boost. Because so as you all know, so the pharmaceutical industry is making lots of money, and so in this picture, so we're showing the top 10 pharmaceutical companies in the world, and the first company is Roche. So Roche is a Switzerland company, and Pfizer is an American US-based company, and AbbVie, and Johnson & Johnson, and Sanofi, and Merck. And so there are a lot of pharmaceutical companies all over the world. But many of them are located in US, and some of them are based in Switzerland. And this is a little bit different, so the statistics, but overall, they're very similar. And the Pfizer, Roche, and Sanofi are the top 3. So the top 10 pharmaceutical companies are making monies about $440 billion, which is amount to about 500 zillion won. So maybe you can convert it. So in 2017. So this is a big industry. However, Korean pharmaceutical companies are occupying less than 1% in global market. So I think so this kind of field can be our next goal, next field. And also so there's one advantage in the pharmaceutical industry, because so it doesn't require any resources. So it only requires a large number of chemists. So it's a really labor and capital intensive industry. So today I'm going to talk a little bit about recent success of lasertinib. So the lasertinib is a new drug candidate, which is not approved yet. So it's a drug candidate still. So developed by Yuhan. So as you all know, this is a Korean company, and so recently there was a news saying that so they sold it to a global company, Janssen, by amount of 1.2. So this molecule, they sold it to Janssen, this molecule, by $1.25 billion, which is about this amount of money. Which is huge, right? Which is a big deal. So this lasertinib, this lasertinib is shown here. The chemical formula of lasertinib is shown here. So that this molecule was designed to be a new drug to treat lung cancers. So, and also, so it has many advantages, and so I'm going to talk about it a little bit more. So here, they're describing their, the advantages of this drug, but so maybe you may understand it, but I'll explain a little bit more detail of this molecule. So this was a big deal, and so it's still under investigation. So this molecule, lasertinib, is targeting EGFR. So the article says that so this binds to EGFR protein, and it blah blah blah. It has some resistance, blah blah blah. So first, so I'm going to talk about EGFR. So what is EGFR? So the EGFR, Have you learned about this in biochemistry class? EGFR? No? So the EGFR is an acronym of epidermal growth factor receptor. So there are many EGFRs in our body. So this is one structure of EGFR. And as you have learned from the last class, so you can find the structure. If you want to see the structure of this protein, so you can search it from PDB, and the PDB code is shown here. So the EGFR looks like that, and the role of EGFR is it transmits signals. So when there's a cell, so let's say that this is a cell, and the cells are generally surrounded by membrane. Right? So they are surrounded by membranes, and actually on membrane, there are many membrane proteins. So it's not just a smooth membrane. There are lots of proteins are stuck here. So these are all membrane proteins, and some of them are EGFR. And what EGFR does is that so it binds to a ligand. It binds to a ligand. So in our body, so signals are transmitted by chemicals. So chemicals are spread, and when specific chemical comes to here, when it binds to EGFR, then so the mechanism, the picture of mechanism is shown here. So the EGFR binds with ligands. Then when it binds to ligand, then it dimerizes. Dimer means the same protein, two proteins got stuck together. So they form a dimer structure, and after that, the C terminal. You know that the protein is starting from N terminal, it goes to the C terminal, ends at C terminal, right? So the C terminal tyrosines are phosphorylated. You know the phosphate group, right? So that you are the senior students in the chemistry department, so I'm pretty sure that you know about phosphate. So the C terminal of EGFR become phosphorylated, especially tyrosines are phosphorylated. So the tyrosines, so the normal tyrosines look like this, right? So the normal tyrosines, so let's say that so this is a normal tyrosine, and then normal tyrosine should look like this. But when it is phosphorylated, phosphorylation means so it binds with phosphate group. So it becomes like this. So the normal tyrosines are phosphorylated. So the phosphorylations are shown in red here. Then once it is phosphorylated, then other signaling proteins recognize this. Then this one binds to here, then this one binds to here, and this one binds, and the signal cascades down. Signal goes down to the cell, inside to the cell. Inside the nucleus, what is inside the nucleus? DNAs are there, right? So the signal goes down to the inside of the nucleus, then DNAs are replicated. So what EGFR signals is that so once it binds to ligands, so it signals to the nucleus, then it tells nucleus that so we have to copy you. You have to copy your DNA, and so we have to work on cell proliferation. So the cell proliferation means so maybe I guess so this word is not familiar to you, so I wrote down the interpretation. So what EGFR does is that so it transmits the signal. So it tells to a cell that so it's time to copy your cell. So when EGFR is turned on, the cells are replicated, and that's why it is called growth factor. So the organism grows and cell growth is. But you can easily think that when this works normally, then everything is fine. But when this is overexpression means that so the proteins there are too much EGFRs than normal situations. So when this is overexpressed, it means that signals are amplified. So the signals become larger. then what it leads to? It leads to cancer. So you know that the cancer is a, you know that the cells are destined to burst, to be born and grow, and after some time it has to die, right? I mean, but cancer cells don't die. So that's the problem of cancer cells. So the overexpression of EGFR leads to cancer. So the cancer is, so some cells are supposed to die, but they don't want to die, then it causes you a problem. Right? So the overexpression of EGFR was one of the well-known cause of cancer. I mean, it's not the only reason. I mean, so it's one of the reasons. I mean, cancer is a very complicated disease, so still we don't fully understand what's the cause of cancer. So that's the basic. So EGFR is one of the favorite targets to treat cancers, especially it is connected with lung cancer. So many companies try to develop lung cancer drugs to treat lung cancer based on this protein. So since we know the structure of the protein, then how does it work? I mean, so as I told you, so this EGFR has to be phosphorylated. Then phosphorylation, how does phosphorylation work? I mean, so you may have learned about this in a biochemistry class, I guess, but what is the source? Where is the source of this phosphate group? Yes, it is ATP. So tyrosine binds with ATP, then ATP becomes ADP, and tyrosine becomes phosphorylated. So I mean, as you know, I mean, so ATP has 3 phosphate groups. I mean, so right, I mean, so it borrows one phosphate group and attach it to a tyrosine. So that's the phosphorylation. So that's where phosphorylation occurs, and most of the proteins associated with phosphorylation related proteins are called kinases. Right? I mean, you learned about this in biochemistry, right? I mean, so the proteins who do phosphorylations are called kinases. So, and there are hundreds of kinases in our body. So EGFR is one of them. So what people thought is that, so this is the structure of EGFR, and here actually ATP binds to here. So people thought that, if we can block that binding pocket with a chemical, with an organic molecule, then we can prevent it from phosphorylation. I mean, so protein, there's an EGFR, and so it gets ATP, and from ATP, it detaches a phosphate group and attaches it to a tyrosine. But if this ATP binding pocket is filled with something else, then ATP cannot bind to this, right? So that's how this kind of the anti-cancer drug for EGFR works. So here, so this is the PDB structure with the ID of 4I24. So this is the structure of EGFR kinase domain co-crystallized with aconitin. So this is another cancer drug. So the drug is already bound here, so the ATP cannot go inside to this protein. And lazertinib and other drug cancers also bind to this pocket. So this means that, so if we know the 3D structure of this protein, then we can design. So what we have to design is that, so some strong binder to this protein. The molecules that binds to this one stronger than ATP. So if this one binds to this, weakly, so it doesn't help, right? So at least, it should bind with this protein, stronger than ATP, so that so it can occupy that pocket instead of ATP. And before lazertinib, and there are many, lung cancer drugs, but there was a problem. So everybody knows that, so we cannot cure cancers, perfectly, completely. So without surgery, right? So one of the reason is that so once you got cancer and once you start to take drugs, then our body adjusts to it, and mutations occur. So in biology, so you know that symbol, right? So T790M. You know that what this means, right? No? So this means that tyrosine number 790 mutates to methionine. So mutations occur in a protein. So the proteins are the sequence of amino acids, right? But amino acids may be changed. One or two or small number of protein amino acids can be mutated. So here this means that tyrosine located at 790 position is mutated to methionine. So when this mutation occurs, the known drugs no longer works. So the people have drug resistance. Then you know what drug resistance is, right? You take drug, but it doesn't work anymore. So most known lung cancer drugs do not work. So if this mutation occurs, so the patients, as they take medicines long time, so they generally, these kind of mutations occur, and so the EGFRs which have this kind of mutations survives, and so after several months, so patients become drug resistant. So it is known that about 40% of lung cancer patients are known to have this kind of mutations. For these people, so the other lung cancer drugs don't work. So for these kind of people who have mutations, there's only one drug, known, whose name is osimertinib. So which is shown here, whose structure is shown here. So the complexity of drug discovery or biology comes from all kinds of these kind of mutations. When mutation occurs, suddenly some type of drugs don't work, and we have to develop new drugs. So there was only one drug for 40% of lung cancer patients. So osimertinib is very popular drug, and because it is the only drug that works for this type of lung cancer. So that's why it is very expensive and very popular. So Yuhan did was that so they started from this drug. So this was known. So this was developed by other companies. So this is being used right now. So starting from this structure, so they thought that so let's develop a new drug based on this structure. So starting from this structure, so if you can design this kind of molecule, then you can make tons of money, right? But which is not easy. So everybody wants to do it, but it's not that easy. If you look at the chemical structures, so they look pretty similar, right? So they have this kind of functional group is the same. This one is conserved, but this group is closed as a ring, and it has ring here, but two-membered ring is here, but it is changed to this type of ring. So they changed it a little bit, but they are showing a similar, effects. And also another noticeable difference from known drug, osimertinib, is that it penetrates blood-brain barrier, in short, BBB. So the blood-brain barrier is a barrier. So let's say that this is a human head, so let's say that this is a human. So we have a brain, right? So I'm not a great painter. So I'm sorry about that. Yeah. So we have a membrane. Membrane covering our brain. So that is called blood-brain barrier. So this barrier is to protect our brain from infection. So other germs and other harmful chemicals. And this is very selective. This membrane is very hard to penetrate. So it is very hard to make drugs that goes into your brain. But the problem is that another problem with lung cancer is that half of the lung cancer patients they don't die from lung cancer itself. So usually lung cancers are known to metastasized. So it means that it moves to your brain. So the half of the lung cancer patients die from their brain disease. Because lung cancer cells, cancer transmits to the brain. So people tested it and they confirmed that this new drug could actually penetrate this blood-brain barrier and it goes inside the brain. And they identified that this laser technique actually can reduce the size of tumor inside the brain. So people are expecting, so people were happy, and so that's why the global company Janssen paid Yuhan about $1 billion. So count about it, $1 billion. So they bought it. They expect that this can be another competitor of this known drug. So that's why they paid that amount of money. So what does that mean? So let's think about what does drug membrane penetration, so membrane permeability. So as I told you, the cell membranes. Maybe you have learned from biochemistry class also. So cell membranes are generally composed of lipids, and they are generally bilayer. So bilayer means this is one lipid molecule, and this is one lipid molecule, and what is this? This is fatty side chain, and this is hydrophilic head, right? So they are forming bilayer, and generally, drugs must penetrate, go through this barrier, go through this membrane. Then think about it. To go through, outside of this membrane, so there's a blood vessel. So the blood goes to here. Then chemicals are solvated in your blood, and it has to go through this lipid, and it has to go into your cell. But think about it. So when it goes to here, so as you have learned from chemistry classes, so these fatty tails are hydrophobic, right? So that's why they are forming bilipid. So if your drug should be somewhat soluble, somewhat hydrophilic in order to be dissolved in your blood, but also it has to be somewhat hydrophobic because it has to penetrate membrane. So the drugs generally should be a little bit soluble, also a little bit hydrophobic. So it shouldn't be not too soluble and not too hydrophobic, nor not too hydrophilic. You know what I'm saying? So if the water is, if a drug is too hydrophobic, then so once you take your drug, so it'll never dissolve in your stomach. So it'll just goes past goes through your body. So it doesn't work. And also, if drug is too hydrophilic, then once you take a drug with the water, then it dissolves in your stomach, but it never penetrates, it never goes into your cell. So it doesn't work too. So it should be somewhat, somewhat hydrophilic, somewhat hydrophobic. So this is the atomic view of model of lipid bilayer. So these are all fatty acid tails, and these are hydrophilic heads. So that's what membrane permeability means. So traditionally, people have designed new drugs based on chemical intuitions. So let's say that so you have this kind of a drug, and this is a known drug, then you want to develop a better one than you think. Then so you draw this one on the blackboard, and you think so okay, so in order to make this, more, effective, so I think I should make this, more soluble. In order to make this one soluble, so how should you change your molecule? In order to make one molecule more soluble, hydrophilic, generally what do you do? So you add more polar groups, right? So if you think about this, then here, sulfur is changed to nitrogen. So more nitrogens are introduced. This one is changed to hydroxyl group. Here, another nitrogen is introduced, right? Then if you compare this and this, then you can easily guess that so this will be more hydrophilic, right? And also, so this one will be extremely hydrophilic, right? So, so this kind of things, so what generally, medicinal chemists or drug companies do is that, so they start from known drug and let's change this part to make it more hydrophilic or to make it hydrophobic, and they synthesize it and they test it, and so which is very tedious and expensive job. So this is the so one example of success. So as you have told you, drug discovery is a very difficult process, but so once you succeed, you can make big amounts of money. So that's why so many companies, especially these days, Samsung, LG, and SK are interested in trying to develop new business for that. And let's briefly review how drug discovery and development process is done. So generally, so drug discovery process goes through these kind of steps. So it starts from target identification. So the target identification means that so here the target means a protein. So target identification means that which protein should we target? So for example, in this. For the previous example, the target was EGFR protein. So once we know the protein, so it's easier to design a drug. So rather than not knowing a target protein. So it starts from target identification, but generally that target identification is for biochemists, not for us. And target validation, so here, so they check so whether that target is really the target. And once we identify the protein, then we start to design or we start to find a drug molecule, drug candidate. So first time, so we find hit. So the hit is translated into Korean like this. So the hit is just the very first stage of molecule, very first stage that can be drug. But these hit molecules can be very toxic. So it's just obtained from very simple experiment. So you just you do this kind of a simple experiment, and you just see that so whether a molecule binds to a protein or not. So once you find the hit, then you make it more, you refine it, and you call it lead. So the lead is the base structure to develop drugs. So at least so this lead has some effects, and it shouldn't be that toxic. So starting from lead, so once you determine a lead, then you change. So then you think. Which functional group should I change? So starting from the lead, then you make changes and you find new molecules. So that step is called lead optimization. That step is called lead optimization. So starting from a lead molecule and you make changes and test it. And after that, see, you do preclinical. So the preclinical means that before clinical trial. So clinical means test against human, and the before clinical means that you test it in a lab and you test it to animals. So whether it works, or at least so animals shouldn't die, right? So before you test it to human. And once it is confirmed to be safe for animals, and then it goes to clinical trials, the real human experiment. And so this is another, So this is the more, there are so where chemistry works is, this kind of step. So here, we find heat molecules. We find heat molecules and make it and refine it based on your organic chemistry knowledge. And once it is done, so it also goes to an animal experiments, so which was done. Oh, knockout mouse. Oh, okay, that's a good question. So the knockout mouse is a 했으니까 내가 한국어 얘기할게. 우리가 어떤 단백질이 이제 질병의 원인이다. 그러니까 이제 질병이라고 하는 거는 그러니까 런 캔서가 있을 때, 뭐 예를 들어서 캔서는 심한 거지만 어쨌든 이제 질병이 있을 때, 그러니까 단백질이 이제 어떤 단백질을 치료하면은 그 질병이 나을 것인가를 지금 이제 여기서는 이제 찾는 거란 말이에요. 그러니까 어떤 단백질 딱 하나를 타겟을 해야 되는데, 그럼 이제 쥐에서 그 단백질, 사람이랑 쥐랑 거의 비슷하기 때문에 대부분의 포유동물 비슷하기 때문에 이제 쥐에서 그 단백질이 있는 유전자를 잘라낸다는 게 나카웃이라는 거죠. 그 단백질이 없는 쥐를 만들어서 이제 똑같은 짓을 해보면은, 그러니까 이제 얘가 이제 있거나 없는 애들은 이제 그러니까 이제 질병이 이렇게 나타나는 그런 현상도 다를 거잖아요. 예를 들어서 이제 내가 어떤 바이러스를 줬는데 이제 어떤 단백질이랑 얘가 이제 상호작용을 해서 이제 질병이 일어나는 거라면 그 단백질이 없으면은 얘는 이제 다른 뭔가 behavior, 그러니까 다른 어떤 증상을 보일 거란 말이에요. 그러니까 이제 knockout 마우스는 이렇게 이제 어떤 유전자를 한두 개씩 잘라가지고 어떤 단백질을 이제 죽이는 거를 이제 knockout 마우스라고 해요. 그래서 이제 이렇게 하고 여기에서 이제 케미컬을 이렇게 이제 우리가 이제 만드는 거예요. So, okay, yeah. So we tested against the animal and we tested to humans. So let's briefly explain about, clinical trial. So once it is confirmed to be safe for animals, then we test it to humans, to real persons. So it's scary, right? So first, so it consists of 3 phases. 3. So the first phase, they tested with 20 to about 80 healthy volunteers. And they inject a new drug candidate, very small amounts, and see whether they are toxic or whether there's any side effects or something like that. So if you are really unlucky, maybe you can have some problems, I don't know yet. So once it is confirmed to be safe, then it goes to phase 2. And also, and the success rate of this step is about 70%. And so the 70% successes, and after that, it goes to phase 2. Phase 2 generally done with, about 500 real patients. So this was done, the phase 1 was done with healthy volunteer, normal person. So this one is done with patients. And here, so you check whether it is really effective or not. So, and once phase 2 is done, it goes to phase 3. Oh, and the success rate of phase 2 is about 30%. So the many drugs fail here actually. And once it's done, it goes to phase 3. In phase 3, so about with 300 to 3,000 patients, tested with 3,000 patients all over the world with ethnic group. Ethnic group means, so we have, white, yellow, and black people, right? So it tested to various people all over the world, to see whether it really works for, everyone. So not just for only a small number of people. And the success rate of this step is about also 35%. So after it is done, then it is approved from FDA, then it can be sold. So if you multiply those success rates, so 0.6%, 70% multiplied by 30%, multiplied 30%, which means at about 6%, which means about 6%. So once you found the, very, plausible, very good candidate, still, so the success rate to pass all these clinical trial is very low. So that's why the drug discovery process is very expensive. And actually, many Korean companies are trying to discover new drugs, these days, so for example, so I brought this from, so one, company, and so they are testing many molecules, many drugs, and as you can see, so there are many, but so fewer drugs are at phase 1, and fewer drugs at phase 2, and fewer drugs at phase 3. So they have about, 1, 2, 3, 4, 5, 6, 7, 9 drug candidates, but so maybe if they are lucky, so maybe among these, so only 1 or 2 drugs will be approved finally. So, and actually, so there were some new drugs, developed by Korean companies, and so there were 29, new drugs, developed by Korean companies, but only 5 of them made more than $100 million. So which is not that much, so because, so the reason for low market share is that, so because, so all these drugs were derived from existing drugs, and unfortunately, there were generally, so there were better drugs than this. So let's say that, so for example, so let's say that, so this one is to treat, diabetes, 당뇨병. To treat diabetes, but still, so there are many other, diabetes drugs. So there are many similar drugs. But the best-selling ones are the best drugs. So they're expensive, but people want to buy, the best drugs. So if it is not the best one, so you cannot sell it that much. So actually, the overcoming existing drug is getting more difficult. So that's another problem. So why is, oops, let me see, oops, oh, yeah. So in order to reduce the amount of money used for drug discovery, so people these days, drug companies are using computers extensively, computers a lot, so that's called computer-aided drug discovery, in short, CADD. So the CADD means computer-aided drug design. And here so I'm showing you so what kind of tests so computers can do. So there are lots of tests. But in this class, so we're gonna practice so especially 3 of these. So the homologous modeling and protein ligand docking, and maybe connected to this one, target flexibility and so protein dynamics. So we're gonna practice so 3 of these so during the class. And then why are computers getting more important these days? So have you heard about the Moore's law? So this guy is Gordon Moore, who founded Intel. And so you know Intel, right? So the company makes CPUs, and so he must be a very rich guy. Anyway, so he said that so there's a Moore's law. So the number of transistors in a dense circuit doubles every 2 years. So the memory or CPUs become twice as faster every 2 years. So that's what he said in 80s, and so Moore's law seems to be correct. So until now, so nowadays, so the CPUs in your iPhone is much faster than PCs in 90s or something like that, right? The CPUs are improved very fast. But the problem of pharmaceutical industry, drug industry, is the opposite. So that's called Eroom's law. So Eroom's law means so if you reverse Moore's law, so then it becomes E-Room, right? Yeah. What it means is that so these days, so this picture, so this plot shows that here the y-axis is the number of new drugs per $1 billion of investment. So if you see these days, so in 2010, so this is the line of one drug, so developed by $1 billion of spending, $1 billion. So if you see this, so these days, in order to develop one drug, so you need to invest more than $1 billion. so the productivity is getting lower because there are mainly two reasons. And so one is developing new drugs are getting harder and harder because in the older days, people, how did they find drugs? They just go outside and cut the trees and cut the plants and just grind it and column it and just find out what's inside. And say, oh, okay, this one may work. And so also, you can see, we have, Oriental medicine book, right? So then you go to, those traditional medicine store and get the plants and extract what's inside. So in the old days, it was easy to discover new drugs, but these days, so easy ones are already all discovered. The easy ones, people have already found easy ones. So these days, we have to find newer ones. And also, so regulations, people care more about health. So in the old days, so people didn't care much about side effects, but these days, people care about health. So the regulations are getting more tighter. So the discovering new drug is becoming harder and more expensive. Oops. So that's why drug companies are trying to use computers to reduce the costs and to shorten the development period. Generally, in order to develop one drug, it takes about 10 to 15 years, which takes very long, right? So companies try to reduce that time period, that time frame. So I'll briefly explain what are these trees. So the first, protein homology modeling. So the homology modeling, homology means similar. Homology means similar. So practically, so we know that protein sequence determines its structure. So proteins are, as I told you, so as you have learned, so the proteins are 1D chain, so long chain of amino acids. When the sequences, the order of amino acids are determined, its 3D structure is determined. So it's unique. But not all protein structures are known yet. So let's say that I want to study this protein, but I don't know its structure. Then what should I do? Then you go to the database and see whether there is a protein which has similar sequence. So basic assumption here is that if two sequences are similar, then structures must be similar. So that's what homology modeling is. So when you don't have your structure, when you don't have the structure of your protein, then you search database and you find the similar proteins and you assume that, because sequences are similar, so the structure of these proteins must be also similar. So from this, you make a model using computer, and this is the model structure. So that's what protein homology modeling is. And the second thing we're gonna practice during the practice session is protein ligand docking. So the protein ligand docking is that, as I told you, many proteins are controlled by binding with a ligand. So for example, so this one is working, but if this ligand binds, then it may stop working. Or sometimes, so the protein is stopped, but once it is bound, it may get activated. It can work both ways. So the docking calculation predicts, how small ligand will bind to protein. So, and as you can see, there are lots of, molecules are bound to a protein, right? So these are all generated by computers. So you predict how will they bind and how strongly they will bind to protein. So that is called protein ligand docking. You heard about docking, right? Sometimes, spaceships do docking, right? So the docking means, two things get combined together. And the last one is we're gonna practice protein dynamics using molecular dynamics simulations. So the molecular dynamics simulation means that dynamics, dynamic means something is moving. So dynamics means that we're gonna simulate how proteins move So as I told you before, still, so even with the best microscope in the world, so we cannot see how proteins move. But using computer, so at least we can simulate how this one will work, how this one will move. So for example, so in this protein, so this protein, so these parts are not moving, but this part is like flapping like this. Or if you start from here, so this is a model membrane, and starting from here, if you run simulation, then after some time, like after 500 nanoseconds, so its structure will change, and so these molecules will go into this membrane or something like this. So we're gonna look at this kind of phenomenon. So we're gonna simulate these, using computers during practice session. So this one is too complex, but during the practice session, at least so we can do this one. And also, so MB can be used to calculate binding affinities, binding free energies between protein and ligand. So yeah, so these three topics are the main topics we're gonna practice this semester. So so today I will try to introduce you so what we're gonna do this semester and why this is important